Hi, it's time for another math easy solution. Today we're going to discuss further into the population growth other models video series for the differential equations videos that I've been going over, and now look at example 3 of that other model series and look at extinction and how to include that into the population growth models. So let's go over this example, which is pretty interesting. So basically this example states there is considerable evidence to support the theory that some species that for some species there is a minimum population M such that the species will become extinct if the size of the population falls below M. In other words, P is less than M. So in many species, if the population is too small, it just won't get bigger and bigger. It will just eventually become extinct, and this is shown. This is known in many different species around the world. So let's look at how to incorporate that into a population growth model. And in this video, we'll just incorporate that into the logistic model that we went over in previous videos. So make sure to watch those. So basically, this condition can be incorporated into the logistic equation by adding the factor 1 minus m slash p, or 1 m divided by p, and I'll explain that in a bit. So basically, thus the modified logistic model is given by the differential equation dp over dt equals to lowercase k, which is a proportionality constant. T is time, p is population size, then times p. Then this is going to be times it by 1 minus p over capital K, where that is again the carrying capacity, and I went over those in previous videos, so make sure to check those out. I'll put all the links in the for my previous videos that are related to this in the description below, so check those out. And then we multiply this. So then the first part of this is the logistic model, and now we're just including this factor 1 minus m over p. So the way this works is this incorporates extinction. That's because we know that p is less than m. So if p is less than m, so we'll write if capital like that. So if p is less than m, what we end up having is this 1 minus this is m. So p is less than m. So this means this number is greater than 1. Yeah. So we're gonna have a number greater than 1 where m over p. Because this is less than, so a number divided by a number smaller than it, that's going to be greater than 1, so this becomes, well, less than 0 or negative. So this means that we're going to have, this is going to go negative, and then the population growth is decreasing. So eventually it will get to 0, and we'll go over that in this video. So now this states, part A says, use a differential equation to show that any solution is increasing if m is less than p less than k, and decreasing is if the population is less than m greater than 0. Yeah, so the first one is the population size is greater than the extinction minimum population for extinction to not happen, and then the less than carrying capacity in K. And we'll go over part B, C, and D in a bit as well. I'll read those out later. So let's just look at part A. Yeah, so part A states, well, so if M is if population is greater than M but less than K. So if M is less than P less than capital K, what we end up having is, well, dp over dt, our differential model. This is equal to, let's put this in brackets, so I'll explain why. So this is k times p, and we're going to have a 1 minus p over capital K, and this is just our 1 minus m over p, and this is double check. Yeah, so that's the exact same model. So anyway, so when we have this, the way we can check if this is increasing, so we want to know if that solution is increasing. In other words, is if the population growth rate is positive. So that's one way we can look at it. So both the, if you recall, the proportionality constant is always positive for population growth. So this equals to, this is going to be a positive. We're going to assume population, there's no such thing as a negative population. Doesn't make physical sense in most cases. So this is going to be positive number right here. And now here, well, what we have is P is less than K. greater than m here. So p is less than k, we're going to have a 1 minus, this is going to be less than 1. So this is going to be greater than 0. In other words, it's going to be positive. Or in other words, this part right here, I'll just write p over capital K is less than 1, greater than 0. Yeah, because p is greater than 0. So now this part right here, p is greater than m. So what we have is a 1 minus and then m over p. If it's greater than it, we're dividing by it. This means this is less than 1, greater than 0 as well. Yeah, because p is greater, yeah, p is positive number, that's also greater than m, so it's just a fraction, less than 1. So what we have is 3 positives. So what this means is this whole thing is a positive or greater than 0. So then the growth rate is a positive growth rate. In other words, p is increasing. So that's the proof for that. And now let's look at the second case of part A, which is show that it's decreasing if p is greater than 0 but less than m. So let's erase this. So what we have here, if 0 less than p less than m, what we end up having now is, and I'll write that down then, dp over dt. What we get now is this kp is going to be still positive. K is as a positive constant. And then what we have here, nothing's really changed here because p is less than m, which is less than k. So then it's still going to be a fraction that's less than 1, but greater than 0. So we have positive, and then the last part right here, if p is less than m, and I already explained that here. If p is less than m, this is less than 0, as I explained earlier, because this fraction is going to be, well, greater than 0 in this case. So this is going to be negative. Yeah, so this is going to be greater than 0 because p is less than a number divided by a number less than it is positive. So this means this is 2 positives and a negative, and this means that we end up having is 1 negative. Yeah, so this whole thing's going to be negative. Remember, odd number of negatives becomes a negative. So this means, well, this is decreasing. P is decreasing because the growth rate is negative or less than 0, like that. And there we've showed it for those 2 intervals. Now let's go over for part B. So part B says for the case where k is 0.08, capital K is 1,000 and m is 200, draw a direction field and use it to sketch several solution curves. Describe what happens to the population for various initial populations. Then it says what are the equilibrium solutions. So let's look at that. Let's write part B. So our differential equation is going to be dp over dt, and it's going to use those same values that we've been using in my previous example videos on population growth. So the little lowercase k is 0.08, and we have p 1 minus capital K, just regular p over capital K, which is 1,000, and now our m is 200. So 1 minus 200 over p. So if we draw a direction field, again, recall direction fields that I usually use this website to graph these out, and again, recall direction fields are simply just the slopes at each point, because just automatically calculated or individually calculated for just any number of points. What you could do, so this is the calculator I use, the GeoGebra.org. You can check that out, and so you basically plug it in here, and then you can graph the y. The y coordinate in our case is p, and the x is t. I'll replace those later. So you plug it in here, you can play around with this, and this is our equation here. And and again, you can learn more about differential equations in my earlier videos. Put the link below as well. So what we get is something like this, which is the slopes at any random point. Then from there we could draw solution curves. Yeah, and here I've copied and pasted that exact same direction field, and I'll just change the axis to t and capital P. So we have something that looks like this, and we're asked again to sketch several solution curves. So let's start off from, well, from here, let's just look at the ones that are flat, which are the equilibrium solution. So this is a flat line. This is actually just P of t for any value is equal to 1,000. So that's one of our equilibrium solutions. And then there's one right here at the 200 mark, which is our m. So this is our m equals 2, and this is our k equals 2, which is interesting right here. And then P of t equals to 200, and that's just a flat line. And now if we start above our carrying capacity, we're going to eventually go back down to this carrying capacity. If we start anywhere like here, so it goes like that. If we start somewhere in between, we're going to go upwards and upwards, etc., and then levels off at the carrying capacity, because you can see the slopes, they're all pointing upward, or they're all positive slopes. Same thing if you go like that. Even if you start off really low, it's going to just follow it along like that. But if the initial population is less than m, if you start somewhere here, look at these curves, they go downwards. This one here, it just goes downwards to 0 right here. So yeah, so when it's less than m, you could see that they go extinct, the population size. Yeah, and here I've written down for each interval. For 0 is for the initial population is between 0 and 200, the population dies out, goes to 0. When population is 200, the population is steady, just flat line. Then between 200 and 1,000, population increases and approaches 1,000. Greater than 1,000, population decreases and approaches 1,000. And the equilibrium solutions are P of t equals to 200 and P of t equals to 1,000. So that's our part B. Now let's look at part C right here. And part C states solve the differential equation explicitly, as opposed to just graphing the direction field out. So those are just rough estimates of it. So either by using partial fractions or with a computer algebra system, and use initial population P of subscript 0, right, like this. So in this video, I'll just go over it explicitly by hand, and I'll use partial fractions. Again, make sure to watch my other videos on partial fractions. And this is a pretty extensive proof of it, or solution to it, just because you know, it's a good exercise to go over this. There's a lot of algebra and manipulations of it, and yeah. So yes, and maybe later I'll look into more of computer algebra systems on it. And I've actually gone over computer algebra systems before, to check those out. I'll put the link below. So let's just solve this equation explicitly. So that's our equation. Again, recall from my earlier video, this is a separable equation. So we have dp over dt equals to lowercase k, capital P 1 minus, this is P over capital K, 1 minus m over p, like that. Yeah, so this is a separable equation because we can move all the p's on the left side and then all the t's on the right side, and then take the integral like I've done many times before. But first thing, let's just simplify this to get rid of these fractions like that. So the way my calculus book does it is it multiplies the right side by p over p, so we're not changing anything, as well as capital K over capital K. So the reason is, now we could bring this in together, so this multiplication can go into this, and then this would cancel with this, but then you'll also have a P right here, so when you multiply that inside, and then we're left with this K, this P right here can cancel with this. So remember, we're not changing anything. This is the same thing as timesing 1 over 1. This whole number is just 1, so we're not changing anything. And now this K, what we could do is, well, this multiplies this inside, so we can cancel this. When you multiply this inside this with this, and then this becomes a K, like that. And then what we're left with is this K value. So what this means is this equals to lowercase k over, bring this over, capital case K, and now what we're left with is capital K minus P times by P minus M. So it's a bit neater and just more clear writing it like this. And now what I'll do is move over this entire thing to the other side, and then bring the dt on the other side. So what we end up having is, we could just divide that out. We're going to have dp, let's write this somewhere here, dp over k minus p, I'll put a capital, let's make it more clear, and then this is m, I'm p minus lowercase m. And then this equals 2, we move the dt on the other side, we have lowercase k divided by capital case K over dt. So now we have it like this. Now we can take the integral of on the left and right side according to each variable, t and this one p. And now to solve this left side, again, this is to integrate it, the best way is partial fractions. So recall partial fractions, write this like that. So if we recall this partial fractions with this 1 over k minus p times it by p minus m, this equals to, well, a over, this is the constant a, over k minus p. So you could separate these fractions into partial fractions, plus b over p minus m. And now we could multiply both sides by this entire denominator, k minus p times p minus m. So multiply that across the board so we can get rid of all the denominators. So what we'll have is on the left side, that's just equals to 1. We're just multiplying it by itself there. And then this equals 2. Then this part here, the k minus p will cancel with this, and we're left with p minus m over, and then times by a. And then the right side, what we end up having is this plus, and then this p minus m cancels with this. We're left with capital K minus p, and then times b. And now we could try to simplify this further and try to solve it directly for a and b, but notice from here what we could do is instead just plug in values. And this is another strategy in partial fractions. You could just plug in values. So plug in values, because remember a and b are constants, so whatever values for p you give, because this p could change, so plug in values for p, because whatever values you have, a and b will still be the same, so it's constant. So what we'll do is we'll write, for the first part, to get rid of this a, we'll write p equals to m. So if it's like that, so let's write if p equals to m, this becomes 0. So what we end up having is 1 equals 2, this goes to 0, and then we're left with this k minus p, k minus m, because p is m, times by b. So then this means b is equal to 1 minus k over m. And remember, b is constant, so it's always like that regardless of the value of p. And now let's look to solve a, and the way to do that is just look at this, just plug in p equals to k, so this cancels. And then what we're left with is, well, if p is equal to capital K, then what we have is this goes to 0, we're just left with this 1 equals 2, and p is capital K minus m times a. So this means, well, divide that out, a equals to 1 over capital K minus m, which is the same thing as b, so that just equals to b, like that. So then what this means is, if both of these are equal to 1 minus k over m, we could write this as equaling 2, and then factor it out, 1 over k minus m, times it by, this is going to be 1 minus capital K over p, plus 1 divided by p over m, like that. And again, that's because the constants a and b are both of them are the same, and it's 1 divided by k minus m. So that is what we could plug in, and we can take the integral of this. The integrals of each of these individually is a logarithmic function. So what we end up getting now is our integral is going to be, and I'll write this down. So this integral right here, we could replace these as partial fractions with this. like that, and then this is a constant. We could take that out of the integral, so what we end up getting is 1 over capital K minus m. Let's write this like that. Integral of 1 minus, and I believe this was capital K minus m, and capital K minus p, and this is p minus m. I'll put a bracket like that. This is p minus m. I think those, let me just go back, it's my bad memory. Yeah, so minus m. So this k minus p, and then this p minus m. And then we could put the dp right here. And then on the right side, nothing's changed. This is still the integral of lowercase k over capital case K dt. Yeah, so now what we could do is, well, let's just solve this. Yeah, so what we could do is I'm going to multiply this part, this k minus 1 divided by k minus m1 to this side, because those are k over capital K are still a constant, and just get rid of this fraction. So I'll do that on the right side soon, but the integrals of these separate ones, this equals 2. This one right here is, recall, this is just ln of absolute value k minus p, but because there's a negative p in there, we put a negative out here, and you can just see it. Yes, if you recall my earlier videos, I'll put the proof below for the derivative logarithmic and the integral of this one. So what you have is, if you take the logarithmic of this is going to be 1 over k minus p, but then you have to do chain rule multiplied by the derivative inside, which is -1, so we have to add this negative to cancel that -1. And then on the right side, this is positive p, so then this is plus ln of absolute value p minus m, like that. And then, like always, you have to add a constant of integration, c1, and then on the right side, this, and then I'm moving over this k minus m onto this side, so we have this k minus m, and then this is constant k over capital K, and then the integral, integral of dt is just t, so we're multiplying by that. Then we always have to add our constant of integration. I'll call that c2. So now what we end up having is this, and then recall my on my earlier videos I went over logarithmic properties. You can divide these out whenever you have actually this is a subtraction, I'll do this on the side. When you're subtracting logarithmic functions like this, what you end up having is a division within those logarithmic functions. So this one could be simplified as basically ln of p minus m. Now you're going to be dividing by ln k minus p, so you're dividing by it. So if you're subtracting, you're dividing. So this is going to be k minus p, like that. And then I'm going to move over the c1 onto the other side and simplify it. So now we have k minus m over k over capital K t plus c, where basically I move the c1 on the other side, where c is just equal to c2 minus c1, and this is just a constant. Anyway, so subtraction of constant is still a constant. And now what I'm going to do is now just get rid of this ln. What we could do is take both sides to the power of e. As a power of e. So this becomes like this, but this in capital bracket like that, so that this lns will cancel. It's another logarithmic rule. And now what we end up having is a absolute value of p minus m over k minus p, like that, an absolute value. This equals 2. This equals 2. Well, whenever you're taking the power of something like this, when there's an addition, this is the same thing as multiplication. So multiplying e over c, and then this is going to be e k minus m, like that. This is lowercase k, but these just to show the difference. Lowercase k over capital K, and then t, like that. And now what we could do is simplify this further with this absolute value. This just means that inside of it could be plus or minus. So in other words, p minus m over capital K minus p is equal to plus or minus e to the c, e power of k minus m, little k over capital Kt. And now we're going to simplify this by, this is still a constant, this plus or minus e to the power of c. This equals to d, I'll write that as d, and I'll change that, then I'll define that soon. This is going to be e to the capital K minus m, little k over capital Kt, where d is equal to, well, just plus or minus ec, and this just equals a constant, like that. And now we could solve for this this constant d, and that's basically by plugging in our value right here at t0. Because we're given, well, we're told to just use at t equals to 0, use p of 0 just to, as placeholder, p subscript 0, p0, like that. So when you plug that in, we can find this d as a function of this initial value. So this means now we're going to have, when you plug that in, p0 minus m, that's this side here, over capital K minus p0. This equals to d, and now this t is 0. So you're going to have e to the 0, where again this is just 1. E to the 0 is just equal to 1, so this all equals to d, like that. So this is the value of d. Yeah, so that's the value of d, so let's plug that in. So what we get is p minus m over capital K minus p is equal to d, where d is this now, p0 minus m over capital K minus p0, and then e to the, and then put that entire value in, so e to the capital K minus m, little k, capital K, t, like that. And now, yeah, so now we have everything we need to just basically solve for p. We just got to simplify this further and do a bunch of algebra. What I'm going to do is write this as, just simplify e to the z, this whole thing, just to be just to make it easier to manipulate everything around. And I'm going to multiply both sides. I'm going to move this denominator onto this side, and then this denominator onto this side, just to simplify it, just to get rid of any fractions. So when multiplying it out of here, we get a k minus p. I'll also write this down. First, solve for p is what we want to find. So solve for p. First thing, move that over, so we have this capital K over p0, times it by p minus m, and then this part on the other side, this equals to capital K minus p, p0 minus m, like that. And then we're going to have now times it by e z, just to simplify it. So instead of writing that down every single time. So now we have this, now we can expand this further, multiply this inside, recall the FOIL formula or FOIL method, you just expand this. So k minus p, k times p, and then k times m, and then p0 times p, and then this is going to be negative times negative plus p0 times m. And then on the right side, same thing, we're going to FOIL, and then include, but we're going to include this ez into each of the FOILs. So k times p0 times ez. Yeah, so that's the first part, and now we're going to do k times a negative m right here, and then times ez. So we're going to have minus k times m ez, and then we're going to have this negative p, p0, and then p0, and then there's the ez over there, and then the last one, this is negative p times negative m, that's plus pm ez. And now the next step to do is basically factor out all of the stuff that have a p by it, and then move it over on this side. So what we'll do is, there's a p, there's a kp right there, so what we'll do is put the p like that, take it out, then we'll have a k inside. Look, the next one is this p0, or negative p0, and then we're gonna move all the way to this side. There is a p over there. Yeah, there's a p over there, so we're gonna take everything out of there. This is negative, so but it's gonna go over here, which is positive, p0 ez, and then on this side there's another p. We're gonna be this positive, so we're gonna subtract it, make it a negative. So negative, we factored out the p. So we move it over, take the p out, and it's going to be negative. So negative MEZ like that. And now the next step is to move all of the stuff that don't have a p inside onto the right side. So the ones that we did move out were, well, we moved this out, this as a p, and then this. So the only ones we're left with is from the right side is this positive km. So moving over, so it's going to be positive km, and this one's going to be negative p0m. And then on this side we have just these two, but we could actually factor out the EZ like that. So what we'll do is, this is going to be positive, and I'll factor it out. So this is kp0 minus km. Yeah, like that, km, and then we have an EZ. So this is simplified further, and now what we'll do is, let's just simplify this one inside a bit more. So we have p, and then this inside here, we could factor out this p0. Actually, no, we can't factor out the p0. There's an EZ there, and there's an EZ there. So it's better to factor out the EZ there. So what we'll do is, we're going to have a k minus p0, that's this first part. And now this EZ, we'll factor that out. So we're going to have a plus, we have a p0, take the p0 and m out, so negative m. We factor out with the EZ like that. And I'll put square brackets around this one, like that. And then on the right side, well, let's just factor out further. This equals 2, take the m out. So factor the m out, put that in front. K minus p0. And then this part, we could factor out the k's out. So plus capital K p0 minus m. And now we have an EZ. Yeah, and now the last thing we'll do is we could just divide this side onto this side, and we have our answer, and also plug in our value for EZ. So what we get is now P of t, our population, is equal to, as a function of time, m k minus p0 plus capital K p0 minus m. And now the EZ, we can just plug that in, so just to save time, EZ is k minus m, then little k over capital K times t. Let me just write that, so it's k minus m. So e to the k minus m, put this as bigger than that, k minus m, let's write that bigger because we have to just show the contrast, little k over capital K t. Let's write this neater again, like that. And then all divided by this entire side on this side there. This is going to be a k minus p0, and then this is going to be plus p0 minus m, and then e to the exact same thing over there. K minus m, make this look, it looks like a multiplication of k minus m, like that. Little k over capital K, and then t. Yeah, now there is our final answer. This is a pretty giant answer like that. So yeah, if you follow along, it's pretty useful to get all the algebra, and it's a good exercise, good mental exercise to go through it all. But you could also, there's a lot of programs online you could do computer algebra systems for that, and I'll see if I can find one for later. But anyways, now let's look at the next part. I think there's a part D. Part D says, use the solution part C to show that P of 0 is less than m. Now, if P of 0 is less than m, then the species will become extinct. And then the hint is, show that the numerator in your expression for P of t is 0 for some value of t. Yes, so let's scroll down and also use that this hint, the numerator is just 0, so I'll explain that in a bit. So basically, let's scroll back down. If part D, if the population is extinct, there's a solution, then there exists a time t where the population is 0. So that's basically what it means if it's extinct. So in other words, we have P of t equals to 0. This means it's extinct. And this is the time t. That's all we need is any time t where it's 0. And again, this equals 2. What I'll write down is, well, this is the same thing as writing 0 divided by any number. So that's why it's looking at the numerator only, just because it's pretty complicated there, the denominator and numerator. So 0 equals any number, and what we'll do is write this as n of t over d of t, which is a denominator. So 0 divided by any number is still 0, so all we have to do is deal with n of t, the numerator. So what we're going to do is, find if the numerator is 0. So find if n of t is equal to 0 at any point. Yes, so let's write down our numerator. N of t is equal to, that's this entire top part, m times k minus p0, and then we have a plus capital K p0 minus m, like that, and then e to the k minus m little k over capital K, and then this is t, like that. So now we're asked to check if it's extinct if p0 initial population is less than m. So if we have this, then the first thing we notice is, well, if we move this around, move the p on the other side, p0 minus m, this is less than 0. So in other words, this part right here is negative because it's less than 0. And now another thing we got to look at is, other thing to look at is what happens when we have n of 0. So n of 0, this just equals to this part right here, m, so that's when when time is 0, or the initial value of the numerator. This is p0 plus, and now we have this k p0 minus m, and then this is going to be e to the 0, which is just, so then that's, you plug in t is 0, e to the 0, that's just 1. So in other words, we're going to be having this number plus this, but we know that this is negative, and k is always positive, so this entire thing is a negative number. So what we end up having is, this needs to be positive, otherwise we're going to have a negative population. So then this part needs to be positive, like that. And in fact, you could actually simplify this further explicitly, just expand this, we'll have m capital K minus p0 m, and then plus capital K p0 minus km. And what we have here is this mk cancels with this, and we're just left with, and factor out the p0, put the k in front, k minus m. And we know that the carrying capacity, well, it's obviously going to be greater than m. So this is greater than 0 because m is less than k. And the reason we're doing this is now we know that initially this value is greater than 0. So thus n of 0 is greater than 0. And now we need to look at what happens at so basically thus this. Now look at n of t as basically the time approaches infinity, because all we need to do is find a value that is equal to 0. But what we could do is just find, as time goes to infinity, if what happens to n of t. If this goes to negative infinity, that means this has to cross because it's continuous. So I'll explain that further. So basically, limit now as t approaches to infinity of n of t is equal to limit t approaches infinity, and now this entire thing right here, I'm just gonna highlight this out and then just copy and paste it to save some time, and put that here, copy, put that here, paste, just to save some time in the writing. So we have something like that. I'll put this in bracket like that. So as it approaches to infinity, well, the first part is just a constant. This equals to this just equals to m k minus p0, and then plus capital K, because there's no t values inside, and we can also take this out of it. This is p minus 0m, and then we have now limit. The only time the t appears is over here. So now we have limit as t approaches to infinity of e to the k minus m little k over capital K t, like that. So we have this, and now this k minus m, again, that's just positive because carrying capacity is obviously bigger than the extinction number m. So would we have this as it goes to 0? This is the same thing as going e to the infinity. Everything is positive and this goes to infinity. So this is going to e to the infinity. In other words, it's approaching infinity, but we also know that this part right here is less than 0, or in other words, it's negative, because that's our that's our p0 minus m, like that, because we're given that the initial population less than m to see if it's extinct. So what this means is we're going to have a number minus negative infinity. In other words, this is approaching to negative infinity, like that. Yeah, and now, so what this all means is, and also since n is continuous, and you can learn more about continuous functions in my earlier video, basically the numerator is a continuous function, because e to the power of whatever is just a continuous function, and this is just an addition. You're just adding something to it, so it's just a simple function that's continuous. Then since it's continuous, there has to be a number t such that n of t is equal to 0, or the numerator is equal to 0, and thus the population, the entire equation there, is equal to 0. And that's because initially the initially the numerator is greater than 0, and then in order for it to mathematically go to negative infinity, it needs to cross that 0 mark. So there is a number t such that it's 0, so that simply means, well, that the species will become extinct. The species will become extinct in that case, because eventually the numerator is going to be 0, which again, the numerator, if it's 0, then the population size can be 0 as well. Anyways, that is all for today. If you learned from this pretty extensive video, and there's a lot of algebra and equation manipulation, which is pretty interesting, and especially adding this partial fraction. So if you follow through, it's a great mental exercise to get this all wrapped around your head, and also how just modifying the logistic equation or any other differential equation for different applications can get you different results and proper models, which is pretty cool. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.